So today's lecture is another look at cryptography, which covers the material from chapter 12 in the textbook. This is harkening back to something that we covered in some detail in chapter 2 on encryption. And we're going to get into a few more advanced topics in this lecture. There's many things that we could cover. Cryptography is a truly deep area of study. We're really just kind of get into a little bit more of the primitives, explore a few symmetric and asymmetric algorithms for crypto, look at a little bit of the math behind digests and digital signatures. We'll talk about quantum cryptography and then wrap up with some notes that apply to technology policy for modern encryption algorithms. So methods of cryptanalysis. These are different ways that you could start performing some kind of an attempt to break some kind of an encryption scheme. Even just a simple attempt to decrypt a single message is a cryptanalytic attack. You're trying to break some encryption. That's cryptanalysis. The two that are most practical are highlighted in bold. Essentially, if you're faced with the task of breaking some kind of encryption mechanism, you want to find either some way to infer meaning without having broken the encryption in the first place, like, for example, the length of a particular message or the frequency of messages as they are transmitted over a pipe. Or you'd want to find some implementation weakness in the actual environment of the encryption for the sender, or frankly for the receiver as well, because those implementation weaknesses are much more likely, but easier to find really than the mathematical problems that you would have in terms of finding a general weakness in an encryption algorithm. Like, people like to think that finding a general weakness is the big threat, but most of the time you're much better off looking for a mistake that would happen somewhere in the implementation phase, either from a security standpoint or a software engineering standpoint. If you could deduce the key by breaking a message and then all of the subsequent messages for modern crypto stuff, that would be kind of rare. It'd be strange. Or finding a general weakness or being able to recognize patterns. It does happen. It's just very rare. And you're much better off going with the more practical attacks. All right, so cryptanalysis, if you're trying to do it, there's a couple of different ways that you can start out, meaning a couple of different inputs that you might be able to use in doing a cryptanalytic attack. The biggest diversion, the biggest branching is if you have only access to the ciphertext, or if you have some information about the plain text. So if you only have access to the ciphertext, then you have to start looking for patterns, similarities, discontinuities, just among as many messages, encrypted messages, that you can find. That's it. That's your only real option. This is sort of what happened with Enigma in World War II. If, however, you have any access to some part of the plaintext, you're probably much better off. And there's three basic variants of plaintext that you might use as inputs to an algorithm that does this, or to an encryption algorithm. A known plaintext attack is where you know exactly word for word what was in the plaintext that produced a particular ciphertext. Okay, and the more pairs of known plaintexts and known ciphertexts that you have, the better off you are. Most of the time, you're not going to have that. Sometimes you will have something like a probable plaintext, meaning we know it's going to be something like this. It's a form letter. There's some common pattern that would happen to be somewhere in that plaintext that we're pretty sure about. And that would be something that would help, but not be as helpful as a completely known plaintext. And then finally, a chosen plaintext attack. Typically, this is only going to happen in cases where you have access to the encryption algorithm itself, and you can decide what your own input is, generate your ciphertext, and then start doing a cryptanalysis attack on the encryption algorithm based on that chosen plaintext. Sometimes you can do this without having access to the encryption algorithm, but those are somewhat rare circumstances. Okay, cryptographic primitives, and we'll talk about the last two in a little bit more detail on this slide, simply because they're very hard to achieve in practice, and they're basically the reason that modern crypto actually works. I'm just going to very briefly cover the first two because we have separate slides on those. So with substitution, you're basically just exchanging one set of bits with another. That's it. So if we're trying to encrypt a message of hello, it would be like taking the H and representing the H with a P. Right? That's a substitution. Transposition is rearranging the order of the message so that you can create a ciphertext by breaking repeated patterns in the underlying plaintext. So if we're trying to encrypt a message that just says hello, maybe we would transpose all of the characters by having it read ELHLO. right? All the characters are still in the message, they're just rearranged in a transposed order. Okay, those are the simple ones, and we will talk a little bit more about those in some detail on the next 2 slides. The more complicated ones are confusion and diffusion. So confusion is the metric that you use for algorithms that have really complex functional relationships between the input, generally a plain text, but sometimes the plain text and a key pair, and the output, which is the ciphertext. So that when you change some part of the input, meaning you change a character in the plain text or you change part of the key pair, you get really unpredictable changes in the ciphertext. So confusion is sort of like if I were to have a message like hello and I encrypted it and then I changed the message where instead of saying HELLO, I said HALLO, I got a radically different ciphertext. Like maybe the first one is only a 12-character ciphertext and the second one is a 64-character ciphertext, and they're not even remotely comparable. That's an algorithm with reasonably good confusion, something that's totally unpredictable in output. And then diffusion, another primitive that works mostly in modern crypto ciphers, is essentially saying that when you change input in the plain text or the key or what have you, this change, even if it's a relatively small change, results in massive changes to the ciphertext. So again, going back to that change where I'm changing the message from hello spelled with an E to hallo spelled with an A, if I had something like that resulted in massively different changes to the ciphertext. Like, example, if I had a message that was 64 megabytes of just plain text, and it started out with those 5 characters, HELLO, and then I decided I was going to change that E to an A, if those changes resulted in an output ciphertext where they were diffused all throughout the ciphertext, right? That one single change made any other possible character in the output ciphertext change, that would be a good example of diffusion. So we're distributing all of the changes from that change throughout the entirety of the message rather than just having some kind of an unpredictable change. Typically, you're going to get both of these. Like algorithms that have good confusion also generally have good diffusion. It's kind of hard to find examples that are skewed widely to one or the other. They do exist, but they're not, particularly common. Okay, so let's talk about those other primitives, the ones that are fairly old and easier to grasp mathematically. We'll start with substitution. Again, this is just replacing a character with another character. And there's a couple of different ways you can do this. One, homophonic substitution, is where you're using more than one character in the ciphertext to represent a single plaintext character. So if I had that same message, hello, and instead of replacing the H with the P, maybe I was replacing it with a P and a G, that would be homophonic substitution, right? Because I'm using more than one character to represent a single plaintext character. Polyalphabetic substitution is when we're actually doing more than one substitution, right? So if you think of a substitution as just a single shift, right? Maybe we're changing every character by 3. Right, so instead of having an H, we would have like a K or something, and instead of having an E, we would have like, I don't know, shifting. What is it? F, G, H. Yeah, we shift it to like an H, right? And then we could shift the L, M, N, O. So we'd have some shift by 3 that would get us to for each of those characters. You can represent a shift by 3 by just using the third letter in the alphabet, right? So you can sort of think of it as I'm encrypting the message hello using a passphrase of just C, and that C applies to every single character in the hello message. Another alternative would be polyalphabetic substitution, which instead of having a single character, you would have a passphrase. So maybe instead of C as your encryption to shift every letter by 3, you would use the word bye, B-Y-E. So we've got hello and bye from goodbye as our password. So the B would be a shift by 2. The Y would be a shift by like 25, 25, and then the E would be a shift by 5. So the first character would be shifted by 2. The second character would be shifted by 25, and this would wrap around the alphabet. And then the last character, the first L in hello would actually be shifted by the last character in our passphrase, which is an E, a shift of 5. And this is a polyalphabetic substitution because instead of having that one shift that applies to every single character, you're using multiple shifts, in this case 3 different alphabets, to shift the characters in a repeating fashion. So that's that second L in HELL, the fourth character in our message, would actually be shifted by B again, a 2-character shift, because B is the first letter of our passphrase, and we would just continue repeating that passphrase and applying it over and over again to our message. So that's essentially the Vigenère cipher, which some of you may have heard of. Polygraphic substitution, the last kind of substitution we want to talk about, is a substitution where you're using a separate ciphertext character to represent multiple characters in the plain text. So if your plain text has a common set of characters that repeat regularly, like one of the most common words in the English language is the word the, right? And if you have the, THE, as a character that you want, as a set of characters in the plain text that you want to represent by a single character in the ciphertext, you can totally do that. It's actually a pretty reasonable way of doing things because that character set, the THE character set, appears many, many, many times. And so you could represent THE by just using maybe D or some other character. Okay, so that's substitution. Let's move on to transposition. Transposition is really just a reordering of characters in some kind of a reversible fashion. So you could do columnar transposition, right? This is one way of doing it. There are many others. Essentially, you take the plain text and then you write it out in rows of some kind of a fixed length, and then write down the columns in order. So in this case, our final exam is on May 18th, and our message would be final exam May 18th. And we'll do this in columns of 4. So we've got columns where each is a column of 4, or just doing 4 characters and then 4 characters and then the next 4 characters and the next 4 characters. Instead of reading it from right to left and then top to bottom, so we'd go right to left, down, and then right to left, and then down, we could actually read it from top to bottom and then right to left, right? So FLM1 becomes FLM1, IEM. Oh, this should be an 8. Last time I taught the class, I think it was the 17th. And this should also be an 8. So we'd go IEM8, and that's your IEM8. And then NXAT, NXAT, AAYH, AAYH. Now you could reverse this fairly easily. I think it's good to sort of think through how would you actually do this kind of reversing in order to kind of get back the original message. But it is actually a reversible technique. And then the last slide in this segment that I wanted to cover is something called a one-time pad. This is mentioned in the textbook as the only way to have perfect security with an encryption algorithm. The problem with this is not the mathematics behind it, because the mathematics are actually perfect. If you have an input that is a legitimate long series of non-repeating numbers, totally randomized, and your plain text, you can exclusive OR your plain text with this long non-repeating series of characters or numbers or whatever they may be to produce a ciphertext, and then you do exactly the same operation in exclusive OR to retrieve the original plaintext using the same sequence of repeating numbers. The real problem is that you're trying to transmit a message. So I can come up with a pretty good set of random characters and XOR my plaintext with it, but I've basically just shifted the problem of transmitting the plaintext securely to a problem of transmitting the sequence of long repeating numbers securely, right? Because my recipient, in order to get back the original plaintext, has to have a copy of this. Right, and if I knew how to securely transmit this, then I might as well just securely transmit the plain text. So, like the way this works in practice is everybody meets in the same location all at once at a particular time, and I give you like a pad of just long sequence of non-repeating random characters, and then every single message you tear off one sheet and use that sheet for that message as a one-time pad, and then we're done, right? Like I would use sheet number 1 to transmit message number 1. You would use sheet number 1, which is identical because we met and made sure they were identical, to recover message number 1. And then for the second message, we'd both do the same thing. Maybe you're sending me a message for that second message. I would just use the second sheet in my one-time pad. But you have to have that physical transfer very early on in the process, or in some kind of a secure fashion. So If we're separated and we don't already have this pre-arranged one-time pad mechanism, then a one-time pad is useless. It's very, very challenging to pull off because, again, you just have to find a way to securely transmit or get on the same page with this long sequence of random characters, which is basically the problem that you were facing with the plaintext that you were hoping the one-time pad would solve, right? And it's worth pointing out that if you already have a one-time pad, you can't transmit another one-time pad, right? It's impossible because you're only getting the same number of characters back. There's no way for me to take a message, encrypt it in a one-time pad, and then somehow shrink the size of it at the same time. You have to have this. You already have to have a one-time pad to use a one-time pad. The other thing that's really important to point out, although it may seem obvious, is this should be a one-time pad. You can't reuse this because as soon as you start reusing it, it's possible for mathematics to help you recover the original the original plaintext given multiple ciphertexts. And that weakens the security of the overall process. So we'll talk about how that mechanism, how the mathematics of that work in the next set of slides.